I want to remind you that when you take your first summative, that you don't want to memorize anything, but you need to understand. You should know all your facts. You should just know them by now. But if you're trying to memorize equations and things like that, it's not going to be helpful. So here are some of my tips for taking the test. First, you cannot game the rubric. Right? Don't just say, oh, well, maybe if I always say do this, it will give me points. Right? Every time I put units, it'll give me points. No. There's no way to know what the rubric is. It's based on many, many, many student answers. And so it's just based on showing who understands what. Your goal is to demonstrate your physics knowledge, not your math expertise. So show me everything you've got when you take the test. For free response questions, because this test is going to have free response and multiple choice, annotate all calculations with words so that I know what you mean. There might be part of the rubric where you explain something even if you have it wrong. If you can't solve, at least explain what you do know about the topic. So maybe there's a VT graph and you can at least tell me the graph slope is acceleration. Put units on every numerical answer. Sometimes it gives you points, sometimes it doesn't. If your approach is taking more than 15 to 20 minutes, you are probably doing it wrong. I call it going down the rabbit hole. Don't do it. So if you are timing yourself and you're doing a free response question and 15 minutes has gone by and you still have lots to do, you're doing something wrong. Stop, go on to another question, come back, see if you can figure out what to do. For multiple choice questions, there's no penalty for wrong answer, so always put an answer. Multiple choice questions should take about 2 minutes per question. Always justify in your mind why you chose the answer. Don't just guess. So at least that way you have a chance of getting it right. There is no partial credit for multiple choice. It's right or it's wrong. Okay, things that you just need to know. You need to know what position is, right? Position is not the same as displacement. So if I am on a number line or something like that, my position could be here. So I start at position of 1 meter. So that would be my position. But if I move to 3 meters, then my displacement, delta x, is 2 meters, right? So don't confuse position with displacement. Speed and velocity are not exactly the same, right? Speed just is how fast you're going, right? So when you're looking at it, if I said I went from 1 to 3 meters in 2 seconds, then you know your speed is the rate that your displacement is changing. So it would be 2 meters over 2 seconds. That's simple, right? 1 meter per second. If I was asking you what the velocity is, the direction, you would tell me I'm going to the right in this case, right? Acceleration is change in velocity. Remember, it's how fast the speed changes. How fast the speed changes. It is not speed. You want to make sure you don't use these words as the same thing. I see students all the time saying their acceleration was high, so they were going really fast. That is not true. So, for example, if I throw something up and it comes back down, it has an acceleration the whole time we know is 10 meters per second. At the top, it's hardly moving, right? V equals 0, but A still equals 10 meters per second. So you can't, lost my second. You can't just say it's going really fast, it has a high acceleration, right? Remember, if you see a negative, that's just direction. Negative is direction. Which way is it going? So if I have a positive A and a positive V, I'm going faster. If I have a negative A and a positive V, I'm going slower. If I have a negative A and a negative V, I'm still going faster, just in the other direction. So same sign, right, is faster. Opposite sign is slower. It doesn't mean, negative doesn't mean going slower. Free fall, we know free fall is 10 meters per second. So it doesn't matter if I throw something up, it doesn't matter if I drop something down, it's all in free fall. As soon as it leaves my hand, its acceleration is 10 meters per second, right? So it's losing it if it's going up, it's gaining if it's going down. I don't care what you're doing, right? It's always the same. Force is a push or a pull. Net force is equal to 0 if we're in equilibrium. So remember, in this chapter, we're staying in equilibrium. Force is in newtons. You know that. Weight is the force of gravity. It never changes. So force of gravity. Remember that it depends on the gravitational field. So here on Earth, it's 10 newtons per every kilogram for that one. Friction opposes motion, right? Friction opposes motion, and so it's going opposite, and this is getting really messy. So let me erase a little bit so we have some more space. You can go back and get things if you need it, but it just gets really crazy sometimes on my little bitty screen. But friction opposes motion. That's the new one we just learned. And so it's always parallel to the surface. So if I'm on a surface like this, friction goes this way. If I'm on a surface like this, friction can go either this way or this way. It's opposing motion, so we don't know. You have to figure out what it's doing. Normal force is always perpendicular, right? So normal force is always perpendicular to the surface. So my normal force would go like this, or my normal force would go like this. It's always perpendicular to the surface. And the coefficient of friction, remember, is not friction. It stays the same no matter what surface you're on. You just did that exercise on friction. And even if you add more stuff, right, to the box and you pull it with a force, well, the friction does increase, right? As the force increases, the friction force increases. But the coefficient of friction, mu k or mu s, is the same. It doesn't change. It never changes. It's a product of what the surface is and what you're pulling it on. So remember when you are doing free body diagrams and you draw all the F's and label them. That was one of the things we were getting lazy about. We got to label them. You got to know what the forces are. That is super, super important. Divide it up into X's and Y's. Add up the X's and Y's. And then set it equal to MA. For this test, it's always going to be equal to 0. So if I have a person and they're standing on a scale, I always draw my free body diagram with the dot in the center. My forces don't float, so I know I have gravity acting down, and I know I have normal force acting up. In this case, I would describe it, right? So I'd say Fg equals force of Earth on person, and then N would be force of scale on person, right? You got to define it, right? You've got to define it because sometimes there's points for that, right? So you want to make sure you're defining what it is and what the force is on which thing, right? In this case, I could write, and it is good practice to do it this way, up is positive, so saying N minus Fg equals 0, so therefore N equals mg. Oh my goodness, that's really hard to read. Let's try that again. So we would write N minus Fg equals 0, therefore N equals Fg, because I'm in equilibrium. Right? If, let's erase, make it less messy. Let's make it so it has something at an angle. So if anything's going at an angle, you divide it up into X and Y's, right? So let's say I have our weight. Remember we had our weight and it was a tie. Let's say it's tied to a string going this way and a string going this way, right? So, well, I shouldn't draw the arrows yet, right? Because it's just a string. So there's some string, it's hanging on top like this. So that's my picture. So then we identify what forces are on it. So that's our first thing. So I'm going to call that T1. Yes, you can call them whatever you want, but some of you are calling it FG to go up, and that just makes no sense. So don't get too crazy on me, but you do have to define it. So if we go there and say, well, that can't be in equilibrium because there's nothing pulling it down. So I know there has to be an FG force going down, right? So that's my first thing. And then I have to define it, right? Fg equals force of Earth on object. Earth on object. And then T1 is force of string on object, right? Because it has to touch it. Remember, all forces have to touch the object to have a force on them. The only exception is Fg because it's a force at a distance. And then T2 is force, well, this would be like string 1, force of string 2 on object. Yeah? So then the next thing is we have to divide it up into its x's and y's. So we would draw a whole new picture. So I'm going to do that in green just so we can see it. So you would have Fg down, and then we can see the components here. We can see the components here, but I want to draw them in x and y down in this picture. So I am going to have T1x going this way, and T2x going this way, and T1y going this way, and T2y going this way. So now I just know everything up equals everything down, and everything left equals everything right. We'll do it as an equilibrium problem just so we see it. So if I was doing these ones, I would say T1x minus T2x equals 0. And then if I did this other one, I wish I had other colors. Let's just do yellow. That works. Then we would have T2y plus T1y equals Fg. And you just start solving. Or, sorry, we should say minus, right? And then you should solve. Always better. Always better. Minus. Oops. Minus. That should be a minus. Oh, because it's the wrong one. Minus, yay, right, equals 0. And then you can solve for it, right? And then you can solve anything, right? No matter what it is. So right now we're staying in equilibrium. So that's the nice thing. Everything's equal to 0. Okay, free body diagrams. Lots to do with it. You should be able to figure it out. I think this is much more conceptual than the kinematics, but we're going to talk about kinematics in a minute. So sample-free body diagrams. I have one going down a ramp. So if I'm going down a ramp, I know that Fg, which is the, I'm not going to keep writing it, but you know that is the force of Earth on the object. N is going to go perpendicular. And then it depends on what this is doing, which way friction goes, because friction opposes motion. So if it is still, and it's just sitting there, and friction's holding it in place, then friction has to be going up the ramp. But if on the other hand, it's moving, let's say it's moving at constant velocity up the ramp. Oops, I can write up the ramp. Right? So if it's moving this way for its velocity, notice I'm not going to draw that on my free body diagram, then my friction would go this way. Right? Now remember, we still got to divide this up into our x and y's. So you see that if we just go back to the red one, let's just concentrate on the red one, these ones, right? We can see that N and F are already perpendicular to each other. So I just need to divide Fg up into the components. So, you know, I have it going like this, right? And so I have, and my xy is now just like this, right? This is my x, this is my y. This is where it gets a little confusing. I know. So N is going like that, and F is going like that. So those are already in my coordinate system, but FGC is pointing down here, right? So we know that going down the ramp is always going to be FG, or in this case, MG, sine theta, and the one going perpendicular is going to be MG cosine theta, right? Or you could do FG, right? Either one works. It doesn't matter. Since we've been using FG right now, let's make it FG. They're the same thing. So this would be FG sine theta, FG cosine theta. So now when I do my equilibrium equations, I can see that in the x direction, I would do those two. So I would have FG sine theta minus F equals 0, and in the y direction, I would have N minus Fg cosine theta equals 0, assuming we're in equilibrium. And I said it was moving, it's either staying still or moving up or down the ramp, right? There's other ways to do it, but that's the equilibrium way, right? We will go on to non-equilibrium later. Right now, we're staying with equilibrium. Okay, let's erase that. The other ones we kind of already did, so I don't know if I really need to do those again. So I think, let's see. So this one over here, we have different forces. So if this is an object, this might be T1, this might be T2, this would be FG, tension from rope 1, tension from rope 2, force of Earth on the object. And then if I broke it up into its components, we'd still have T2, FG, T1Y, T1X, and we know this would be equal to T1, that's my Y, so that'd be sine of theta, and this would be equal to T1 cosine of theta. Terrible, terrible writing. Tell Miss Demas to write better. Let's try again. T1 sine theta. And this one, T1x, would be equal to T1 cosine theta. Yeah? Oh, what about this one? It's just hanging right there. If it's in free fall, what is the only force acting on it? Just Fg down. That would not be in equilibrium. So we talked about on the one we did where it was at terminal velocity. Remember we did terminal velocity? So that just meant that there's air resistance going up. Right, which you can call R, or you can call F air, whatever you want to call it, right? So this would be equal to the force of air on object. And this one would be the force of Earth on object. I can throw any free body diagram problem at you, and you should be able to figure out any of the forces, figure out the total force, figure out anything, right? So you could figure out T1x, you could figure out T1y, you can figure out T1, you can figure out FG. I can make any of them unknown. You have to figure out the rest of it. Okay? Make sure you really review your graphing facts. I'll go over a few here, but just go through everything. So remember, a position time graph, you always want to look and see what kind of graph it is because people confuse, but this is a position, this is a velocity, this is an acceleration. So remember that the y-axis here tells you the position, the y-axis here tells you the velocity, and the y-axis here tells you the acceleration. You should be able to go from one to the other. Remember all the exercises we did? So for example, if we had something moving away from the sensor at a constant velocity, it would look like this. Away from the sensor at a constant velocity, it would look like this. Away from the sensor at a constant velocity would look like that, right? We didn't do a lot of AT graphs, but they're always going to be flat. There's not a lot. The most common ones are position and velocity, but I do sometimes see them doing acceleration graphs. So let's look at another one. Again, you should go over all of them. I'm just going over a few of them. What if we have something going away from this? Actually, let's go towards the sensor, and I'll move this to the 0 point is up here. So if we're going towards the sensor and slowing down, going towards the sensor and slowing down. So that means if we're going towards the sensor, we're starting up here, right? And if it's slowing down, it's going to start steep and then it's going to go slower. That's a terrible graph, but you got the idea, right? High slope, low slope, going towards. If it was going towards the, well, let's just leave it at that. And then for the velocity, if it's going towards the sensor and going slower, it's got a positive it would have a negative velocity, right? So let's put it up here. It would have a negative velocity because it's going towards the sensor, it's going the other way. And so it would have it would start fast and then it would go slow, and the acceleration is going the opposite. So notice here, right, we have negative velocity, positive acceleration because we have a positive slope, right? And so for this one, it would just be, if this was my 0, right? This is just being my 0. If it was positive acceleration, it would be up here. But there are so many different ones I can do. I don't want to do all of them. Go back and look at your exercises. So you need to know what it looks like. Towards the sensor, away from the sensor. Going faster, going slower. Remember, when you're looking at displacement, it's the area. Oh, not there. Don't do it there, right? The area is not there. And that is a common mistake, is you just want to go under the graph, right? Under the curve. But remember, the area is the area bound by the axis. So this would be a negative delta x, right? Because it was moving towards the sensor. So it's moving in the negative direction. So if I know it started at 2 meters, wherever it was, it'd be going in the negative direction. So minus whatever the delta x is the final position of where it ended up. So think about what you're doing. Think about what you're doing as you do it. And like I said, there's so many different combinations. I'm not going to cover all of them, but you should know all of those graph facts. Okay? All right, algebraic calculations. So this, I think, is more mathy, and this is the part that gets a little difficult. But the important thing is always to go through the method. What part of motion are we talking about? From where I kicked it to the top, from the elevator's door to the carpet, or whatever it is, right? Which way is positive? Most of the time we make it up, but sometimes everything's going down. So then you can make the positive direction down if you want. Make your table. You should have that known, right? You should know there's V naught, there's VF, there's T, there's delta X, and there's A. Find your equation. So I handed out the equation sheet. You'll notice they're a little more complicated than the ones I gave you on the fact sheet, but they're the same equations. So take a look at them. If you know 3 of these variables, you can find the 4th, whichever one it is. And usually you only need to find the 4th and you don't need the other one, whatever it happens to be. So you usually know 3 and then you have to find the 4th. But remember, it's not as simple as just like plug and chug and figure out the answers. What they love to do, and this is the part that drives you guys nuts, is derive equations. So if they say derive an equation with X and V, I can't use any equation with T in it because it didn't say anything about T, right? If it says derive an equation with A and X, then that's the only thing you can use. It'll say you can use known constants. The only known constant you know right now, known constant, is G. You can leave it as a G. You do not have to write 10 meters per second per second. Leave it as a G. Don't make a mistake. Okay. Remember, if one of these is 0, it just goes away. So if you're looking at equations, for example, VF squared equals V naught squared plus 2 a delta X, and one of them is 0, it doesn't matter which one, say that one's 0, you just end up with V naught squared is equal to negative 2a delta X. And the way we wrote it on there with delta X is we just said delta X is equal to V naught squared over 2a. Yes, there's a negative in there. That's just telling you direction, right? But because V naught squared, it doesn't really matter. Okay? So make sure the equations make sense, right? Any equation I gave you should be able to work. Make sure to follow this method that we've been practicing. Make sure to read every single word. Okay, hope this helps.